Let's say that we have some function f of x right over here, and let me graph an arbitrary f of x. So that's my y-axis. That is my x-axis, and maybe f of x looks something like that. And what I want to do is I want to approximate f of x with a Taylor polynomial centered around x is equal to a. So this is the x-axis, this is the y-axis. So I want a Taylor polynomial centered around there. And we've seen how this works. The Taylor polynomial comes out of the idea that for all of the derivatives up to and including the degree of the polynomial, those derivatives of that polynomial evaluated at a should be equal to the derivatives of our function evaluated at a, and that polynomial evaluated at a should also be equal to that function evaluated at a. So our polynomial, our Taylor polynomial approximation, would look something like this. So I'll call it p of x. And sometimes you might see a subscript, a big N there, to say it's an nth degree approximation. And sometimes you'll see something like this. Sometimes you'll see something like n comma a to say it's an nth degree approximation centered at a. Actually, I'll write that right now. Maybe we might lose it if we have to keep writing it over and over. But you should assume that it is an nth degree polynomial centered at a. And it's going to look like this. It is going to be f of a plus f prime of a times x minus a plus f prime prime of a times x minus a squared over, either you could write 2 or 2 factorial. They're the same value. I'll write 2 factorial. You could write a divided by 1 factorial over here if you like. And then plus, you go to the third derivative of f at a times x minus a to the third power. I think you see where this is going, over 3 factorial. And you keep going. I'll go to this line right here, all the way to your nth degree term, which is the nth derivative of f evaluated at a times x minus a to the n over n factorial. And this polynomial right over here, this nth degree polynomial centered at a, it's definitely f of a is going to be the same, or f or p of a is going to be the same thing as f of a. And you can verify that because all of these other terms have an x minus a here. So if you put an a in the polynomial, all of these other terms are going to be 0. And you'll have p of a is equal to f of a. Let me write that down. P of a is equal to f of a. And so it might look something like this. And it's going to fit the curve better the more of these terms that we actually have. So it might look something like this. I'm trying my best to show what it might look like. And what I want to do in this video, so this is all review. I have this polynomial that's approximating this function. The more terms I have, the higher degree of this polynomial, the better that it will fit this curve, the further that I get away from a. But what I want to do in this video is think about if we can bound how good it's fitting this function as we move away from a. So what I want to do is define a remainder function, or sometimes I've seen some textbooks call it an error function. And I'm going to call this, I'll just call it an error. So let me just so you're consistent with all the different notations you might see in a book, some people will call this a remainder function, and sometimes they'll write a remainder function for an nth degree polynomial centered at a. Sometimes you'll see this as an error function. The error function is sometimes avoided because it looks like expected value from probability, but so you'll see this often. This is E for error, R for remainder, and sometimes they'll also have the subscripts over there like that. And what we'll do is we'll just define this function to be the difference between f of x and our approximation of f of x for any given x. So it's really just going to be, do it in the same colors, it's going to be f of x minus p of x, where this is an nth degree polynomial centered at a. So for example, if someone were to ask you, or if you wanted to visualize, what are they talking about if they're saying the error of this nth degree polynomial centered at a when we are at x is equal to b? What is this thing equal to, or how should you think about this? Well, if b is right over here, so the error of b is going to be f of b minus the polynomial at b. So f of b there, the polynomial is right over there, so it'll be this distance right over here. So if you measured the error at a, if you measured the error at a, it would actually be 0 because the polynomial and the function are the same there. F of a is equal to p of a, so the error at a is equal to 0. And let me actually write that down because that's an interesting property and it'll help us bound it eventually. So let me write that. The error function at a, and for the rest of this video you can assume that I could write a subscript. This is for the nth degree polynomial centered at a. I'm just going to not write that every time just to save ourselves a little bit of time in writing to keep my hand fresh. So the error at a is equal to f of a minus p of a. And once again, I won't write the sub n sub a. You can assume it. This is an nth degree polynomial centered at a. And these two things are equal to each other. So this is going to be equal to 0. And we see that right over here. The distance between the two functions is 0 there. Now let's think about something else. Let's think about what the derivative. Let's think about what the derivative of the error function evaluated at a is. Well, that's going to be the derivative of our function at a minus the derivative of the first derivative of our polynomial at a. And if we assume that this has more than, if this is higher than degree 1, we know that these derivatives are going to be the same at a. You can try to take the first derivative here. If you take the first derivative of this whole mess, and this is actually why Taylor polynomials are so useful, is that up to and including the degree of the polynomial, when you evaluate the derivatives of your polynomial at a, they're going to be the same as the derivatives of the function at a. And that's what starts to make it a good approximation. But if you took a derivative here, this term right here will disappear. It'll go to 0. I'll cross it out for now. This term right over here will just be f prime of a. And then all of these other terms are going to be left with some type of an x minus a in them. And so when you evaluate it at a, all of the terms with an x minus a disappear because you have an a minus a on them. This one already disappeared, and you're literally just left with p prime of a will equal to f prime of a. And we've seen that before. So let me write that. So because we know that p prime of a is equal to f prime of a, when you evaluate the error function, the derivative of the error function at a, that also is going to be equal to 0. And this general property right over here is true up to and including n. So let me write this down. So we already know that p of a is equal to f of a. We already know that p prime of a is equal to f prime of a. This really comes straight out of the definition of the Taylor polynomials. And this is going to be true all the way until the nth derivative of our polynomial is evaluated at a, not everywhere, just evaluated at a, is going to be equal to the nth derivative of our function evaluated at a. So what that tells us is that we could keep doing this with the error function all the way to the nth derivative of the error function evaluated at a is going to be equal to, well, that's just going to be the nth derivative of f evaluated at a minus the nth derivative of our polynomial evaluated at a. And we already said that these are going to be equal to each other up to the nth derivative when we evaluate them at a. So these are all going to be equal to 0. So this is an interesting property, and it's also going to be useful when we start to try to bound this error function. And that's the whole point of where I'm going with this video and probably the next video, is we're going to try to bound it so we know how good of an estimate we have, especially as we go further and further from where we are centered, from where our approximation is centered. Now let's think about when we take a derivative beyond that. So let's think about what happens when we take the n plus 1th derivative. So what's a good place to write? Well, I have some screen real estate right over here. So what happens if I take what is the n plus 1th derivative of our error function? And not even if I'm just evaluating it at a, if I just say generally the error function e of x, what's the n plus 1th derivative of it? Well, it's going to be the n plus 1th derivative of our function. It's going to be the n plus 1th derivative of our function minus the n plus 1th derivative of our, we're not just evaluating at a here either. Let me write an x there. Of our function minus, I'm literally just taking the n plus 1th derivative of both sides of this equation right over here. So it's literally the n plus 1th derivative of our function minus the n plus 1th derivative of our nth degree polynomial. The n plus 1th derivative of our nth degree polynomial. I could write an n here, I could write an a here to show it's an nth degree centered at a. Now, what is the n plus 1th derivative of an nth degree polynomial? And if you want some hints, take the second derivative of take the second derivative of y is equal to x. It's a first degree polynomial. Take the second derivative, you're going to get 0. Take the third derivative of y is equal to x squared. The first derivative is 2x, the second derivative is 2, the third derivative is 0. In general, if you take an n plus 1th derivative of an nth degree polynomial, and you could prove it for yourself, you could even prove it generally, but I think it might make a little sense to you, it's going to be equal to 0. It is going to be equal to 0. So this thing right here, this is an n plus 1th derivative of an nth degree polynomial. This is going to be equal to 0. So the n plus 1th, let me write this over here, the n plus 1th derivative of our error function, or our remainder function we could call it, is equal to the n plus 1th derivative of our function. And so what we could do now, and we'll probably have to continue this in the next video, is figure out, at least, can we bound this? Can we bound this? And if we are able to bound this, if we're able to figure out an upper bound on its magnitude. So actually what we want to do is we want to bound its overall magnitude. We want to bound its absolute value. If we can determine that it is less than or equal to some value m, so if we can actually bound it, maybe we can do a little bit of calculus, if we could keep integrating it, and maybe we can go back to the original function and bound that in some way, if we do know some type of bound like this over here. So I'll take that up in the next video.